Hello.
Good morning.
How are you?
Doing well, thank you.
Good. Good. All right.
Hi, good morning today.
Good morning.
Hey, Frank.
Hey, Frank. How are you?
Hey, I'm good. Thanks for having me.
Good.
Yeah.
Glad to have you. So I'm gonna mention some stuff that was really kind of fun. Yeah, here it is. Okay. Um, oh, that's not it. Hang on. There we go. Okay. Oh, that's not it either. Let's try this one. There we go. Okay. Let me do a screen share. And then, so I've mentioned this draft before and made it available. So because of the way we're doing in the ladle work, because of the way we're doing rely guarantee and the corresponding notion of negations, and uh, because we insist on interactive systems, the this aspect of the type system, using the rely guarantee ideas, will support properties that are idempotent with respect to the term constructors that give a red X. So, and I just want to give sort of talk about what that means a little bit. So, just to remind people, the basic idea is we've got some kind of resourced type theory. Hang on a second. Shoot, I think Mike did some. Ah, here we are. Okay. So is that large enough? Can people see that? Maybe it's. Maybe I should bump it up. There we go. Okay. All right. So we've got an interactive rewrite system, and the simplest version of the interactive rewrite system is. Hang on, let me turn on. Do not disturb. Is one where you've got just a single rewrite rule, like in the lambda calculus, you have beta reduction, or in the row calculus, you've got the com rule, and then you have a bunch of rules that say how the com rule works in context. But the com rule is the real engine. So you've got a single rewrite rule, which means, and that rewrite rule on the left-hand side of it has got to be a term constructor that's at least binary. So here's your term constructor. Here's the source of your rewrite rule row. And here's your target of the rewrite rule, which is going to be some function of the terms T and U. So K is some term constructor that's at least binary. And then we want at least one generator. And then we want either a left identity or a right identity. Or if we have both, then they have to coincide by elementary algebra. So this is the minimal theory that Ladle will work on. It can be richer than this, but this is the bare minimum that we have to have. And the interesting thing is that it's for these rules to just work them out so people get a sense of it. We've chosen one of the identities as essentially representing the property that the type system will hold for, when all is said and done, when the process is done, and throughout each of the steps, this property holds. Now you can see why that has to be, because essentially when we go through the steps, so here's the first thing that we do is we equip the theory with a resource, and then we change the rewrite so that the source of the target has to have the resource in it. The source of the rewrite has to have the resource in it. And then that means that if you deny the resource and you just have this, then you've essentially got a data structure, which is like a tensor. And then that tensor, in order to really justify being a data structure, we have to be able to pull those kinds of things, the data in that's locked up in here out. So we have a parallel extractor and we have a serial extractor. And that becomes clear what that means in the typing judgment rules. But that's so we add those two term constructors. So that's enriching the overall theory. So initially the theory only had one term constructor. Now it has three. And then there's an evaluation context, which is your resource. So that's the general framework. And then to that, we add a notion of context. So essentially you can knock a hole in a term. So here's just the hole. So it's a constant, right? So it starts from nothing and generates this terms with holes in them. And then you can put a hole in the left-hand side, or you can put a hole in the right-hand side. And then you can close up holes either on the left or the right. And you have a notion of substitution for terms that actually have holes in them, and you have that is implemented in terms of a notion of substitution of a term into a hole in the context. So these things, this only makes sense for banged terms in the same way that substitution or application only makes sense for lambda terms in the lambda calculus, or for comprehensions in the row calculus. So that's the evolution of the different theories. And now the thing that's interesting is that with these notions, we can build up this rely guarantee idea. So the rely guarantee, moving from left to right, is just all those terms that are banged contexts on the right, so that whenever you have a U prime in tau, then when you if there exists a rewrite from plugging the hole here with the U tau that rewrites to V, then V has to be in tau prime. And of course you have the reflexive version. So what that's going to do is, at the end of the day, if we look all the way down, say here, and look at what it means to run something in parallel. I mean, not run something in parallel, but to do a parallel extraction. So we have these type sequences where gamma is a typing context, and that's enough to establish that this thing is typed this way, and delta is another independent typing context, and that's enough to establish. So we read the turnstile as thinks that. So you would read this in English. Gamma thinks that the par of T prime and U prime is of type, rho par, tau perp, tau prime perp. And then if delta thinks that K of TU is rho tensor, tau prime. Notice this is the perped version of that, and this is the perped version of that. Then we're going to form a K with this one, and a K with this one, right? And now is the point about the idempotence of the property, right? So ultimately, this is going to yield a version of the property, and this is going to yield a version of the property. And so in order to end up with the property that you want, and it could be the identity, it could be LK, it could be RK, those are both idempotent. The important point here is that the property is idempotent, because you end up with the property in one of these, and in fact you end up with them in both of them, and so you have to end up with that property over here. And that's the critical thing. So if you think about it, the identities have that. So in the case of the row calculus, the identity is 0, right? What that means is that you, the thing that you could think of it as termination, because that's what 0 means, but really what it is isolation. So what it's saying is that we're going to guarantee the property, the thing in the left or the right. If you substitute this thing in the left or the right, the two components of the system won't mess with each other. That's really what it's talking about. It's giving you this kind of isolation property. The other way, another way to think about this is in terms of, it's not just identities that would work. Anything in the row calculus that is banged has this idempotency, right? So bang P is even structurally equivalent to bang P par bang P. So all properties that are persistent in that way, in those kinds of calculi, are perfectly fair game for the kinds of properties that the type system preserves. So you can think of this idempotency as a requirement, as a kind of persistence requirement, which I think is really quite interesting. It's a really, it's revealing in terms of what the type system does. So that's a lot to digest. So let me stop there and see if that makes sense to folks.
I'm trying to think about this as, so this will not change. So these two terms are not connected in a sense that
you can't mess with each other, right? So
yeah.
So it's like in the case of high calculus, it would be like you have new scopes around the terms, so that any terms that any free names that they might have in common are separated by the new scopes.
I see.
In the case of lambda, you can think of it
like,
go ahead.
Like another function with creating new scope, or
Function.
I mean, new scope with new variables.
Yeah.
I see this similar to new in rolling.
Yeah, that's correct. Right. So it's and isolation is exactly a property that you want, right? Isolation, at least in these kinds of blockchain systems, isolation is absolutely the thing you want to be able to guarantee.
Yeah.
Because then things can really run in parallel. But it can be a very sophisticated isolation, right? Any sort of banged process, which is either a recursive or replicated process, can serve as one of these persistent properties.
Banked in a sense of
The pi calculus.
when,
The pi calculus.
okay, okay.
Yeah. Yeah. Well, that's really all I wanted to share. And this is, I find this work really compelling and engaging. And I was really delighted to be able to give a crisp characterization of precisely the kinds of properties that the type system guarantees.
Yeah.
Frank, does this make sense to you?
Not exactly. I'm still kind of lost on just the general aspect of having terms be spoken in logic. I've actually never taken a logic class. I do have mathematical backgrounds, so I do understand just the basic mathematics of it, but it seems like the logic side kind of slips away from me.
Sure, no worry. So don't think of it as a logic, think of it as a type system. So these are our types. So you could think of this, so every type tau is either the top type, you know, like in Java, that would be object, or an arrow type, and there are two different kinds of arrows, right? So this is, in the lambda calculus, this is equivalent to the function type. Just that we also have a backwards function type in a certain sense. You have types that correspond to generators, right? So these would be like singleton types. So this picks out, like if you have some singleton value, and this picks out the singleton, that this type picks out that one value. Then you have the empty type, so nothing inhabits this type. So that's void in Java. And you have a way of, since types are collections, you can kind of combine them. So you can think of this as like an OR type. This type is saying that whatever you got has been resourced, right? So it's inside an evaluation context. This type says that, you know, you've got two different types, and then you make a new type out of it using the K. And then you have types for each of the different parallel and serial extractions. So this is going to be a version of, this is like K, but with more information that you're going to extract stuff. This is K without any information about extraction. This is K saying we're going to extract stuff in parallel. This is the extractor, the parallel extractor. This is K saying we're going to extract stuff in serial. And this is the serial extractor.
And then how does this relate to the actual ability to come to consensus on a new block? I feel like that's something I'm struggling to comprehend.
So this is about, you can think of these as modular, right? This is not about consensus. This is about the computational model that you're going to run consensus over. So these are types for a language that you're going to, or a virtual machine that you're going to get a bunch of different instances to agree on. Now, how they come to an agreement is an independent question from the fact that whatever notion of computation you're running has to be safe with respect to denial of service. So the way you make it safe with respect to denial of service is you provide a resource, right? Like up here, we have just some ordinary rewrite system, whether it's Lambda or Rho or, you know, Solidity or the Java virtual machine. It's some ordinary rewrite system. And if you run consensus on an ordinary rewrite system, that's all well and good, but it means that an attacker can come along and put in programs that run forever. Does that make sense?
Yes. So it's preventing DDoS attacks and preventing that continuation of, say, an ever-going loop.
That's right. So here's the rewrite system you gave us, or that is input to our algorithm. And our first step is to generate one that has a resource, right? So this resource, resourced version, here's the resource. It says you can only rewrite if you've got some of that resource. Otherwise, you're not able to rewrite. So this is adding gas to the EVM, or adding phlogiston to the row calculus. Does that make sense?
And that resource, would then that resource be the Rev token? Would that be the natural staking token to actually have a resource?
The Rev token turns into phlogiston. So the price of phlogiston, in the same way that gas is not the same as ether, right?
Yeah.
Ether turns into gas. You buy gas with ether. So you buy phlogiston with Rev. So R is the phlogiston. But it's
okay. That makes more sense now.
Sure. And so now once you have that, then you can the next step is we have to be able to talk about context, right? Because we want to be able to do rely guarantee. So the contexts are all about, you know, being able to supply a program that guarantees, you know, a certain type, or so that meet sort of, if you can rely on this program meeting this type, then I can guarantee that the total system meets this other type. And that's what these things are. The arrow types are all rely guarantee notions.
And then just one more question. Do namespaces play a role in this, or is it just the types?
Namespaces do play a role in this. And this is what we were talking about in terms of isolation. So what this type system guarantees is a kind of isolation. And in the case of pi calculus and row calculus, the way you get isolation, the way that's implemented, is in terms of namespaces. The only way for a pi calculus or a row calculus, two row calculus programs to interact is if they have a common name over which they can communicate. And the way you would isolate them is by shoving them into separated namespaces. Does that make sense?
Yeah, that clears the air.
Cool. Awesome. There is one other interesting trick that we did in the last week that I might mention. So notice that in the paper there are two different flavors of these type assignment, type judgments. So the shape of every type judgment is going to be a typing context, your turnstile, a term, and its type. Okay, so you always have a single term on the right of the turnstile in the intuitionistic versions of the types. So you might have lots of stuff on the left-hand side, but there's only a single thing. So this basically makes the turnstile into a kind of function. Lots of inputs, one output. Right, and that's exactly what we see here. So I have two typing judgments. Right, gamma thinks that T is of type tau, and delta thinks that U is of type tau prime. Then when I do my, I can make a K out of a T and a U. And that is, I take everything that gamma thinks and everything that delta thinks together. So lots of inputs, the gamma and the delta. Together, they think that KTU is of rho tensor tau tau prime. Right, so basically, all we did was we took T and U, we packaged them up in K. And so therefore, tau and the tau prime have to show up in the type. And this is the indication that they're ready to be extracted. And we know that because there's no R being supplied. If there were an R supplied, then the thing could reduce. Since no R has been supplied, this thing is a data structure. And so it's available. So the data inside is available for extraction. So essentially, this makes the system reflective, right? So we started with a system that was not necessarily reflective, and this turns it into a reflective system because it suspends the K computation. The K computation cannot proceed without the resource. So since it doesn't have the resource, this is suspended. But notice, this is all the data you need in the original system to run a computation. You just need a K of T and U, and then you can run some computation, right? So this is a data structure that talks about computations. That's why it's reflective. And then when you do a cut, and by the way, the par that is dual to this is just saying, I'm going to extract out of one of these things. But we don't extract willy-nilly. The way we extract it is to, if I have a par that's got a T prime and a U prime, and I have a K that's got a T and a U, then I'm going to form sub-Ks, taking this one with this one, in the case of the parallel extraction, and this one with this one. And then we can also do a serial extraction where we go these two, and then K over all of that. So that's the difference between wiring things up in serial versus wiring things up in parallel. Right, so it's just like Christmas lights. Or electrical circuits, more generally. So anyway, the point is, when we do an extraction like that, we supply the R, and that's enough to run things as we wish. So the overarching point is that we can now do this is reification. So when we did this, we reflected now, and then we have the ability to manipulate, to extract the data and manipulate it, and that's the reification. Right? So these three things together represent the reflective capacities of reflection and reification. And all of that was implicit in taking a theory and adding a resource which suspends computation. And it took me a ridiculously long amount of time to see that. Now, the other point is, the thing that was really cool is that we can, what happened? There it is. So we're going to, we can also do, notice in the intuitionistic case, many inputs, one output. We can also do a classical case, like classical linear logic, where we move things like this to this side of the, because they'll end up being symmetric. We move these things over to this side of the turnstile. So the turnstile is only one-sided. So the sort of standard axiom, which is, if you give me a thing of type T, I can give it back to you, right? That's the axiom. If you hand me a thing of type T, I can give back to you a thing of type T. That's a reasonable axiom, right? It feels like a minimal amount of risk to make a statement like that. It appears to be self-evident. Unless there's something magical about the notion of giving and taking, then unless there's some weirdness in that idea, this is a very natural axiom. So we can convert that into an axiom like this, where it says, I require a thing of type T in order to produce a thing of type T. In other words, they must come in pairs, right? It's like a particle and antiparticle, right? Where again, it's a kind of conservation property that the type system guarantees. And the comma on the right-hand side is interpreted as making a K. So we get so the interpretation of this is K of two holes. One, which is the undoing part of this, and this is the doing part. So K of these two should just go to our property, which is this isolation property. And so what we need in order for things to work out is a contextualized version of the theory that allows for these two-hold contexts as opposed to one-hold contexts. And I kind of screwed it up in earlier versions, but this is the correct version. Or a correct version. There might be others, but this is the only one I could think of that works out nicely. So instead of having just a single hole, we have a white hole and a black hole, right? And that's reflected in the three different types. So you can have a white hole, a black hole, or you can have things with pairs of white and black holes. So this is the constant for the white hole. This is the constant for the black hole. And then we have, if you give me a white hole and a black hole, I can give you one that has a white hole and a black hole back in it, right? So that's the basic axiom, right? Right, K of a white hole and a black hole. That's our basic axiom. And then if you give me something with two holes in it, I can put it in the right-hand side of a K. Or if you give me something with two holes, I can put it in the left-hand side of a K. Or I can close up a white hole, or I can close up a black hole out of a pair, right? So if I have two holes, I can close up the black hole, or I can close up the white hole. If I have which means now I have a system with only one hole, so now I have to be able to close up those, right? So I can take something that is a context and has a single hole to just a term. So this is like lambda abstraction. So we were basically doing abstractions in stages, and that gives us the contextualized version of the Levier theory. So notice, for those people who are sensitive to all the stuff that goes on with nominal theories, I'm being super, super conservative. I'm not introducing a nominal theory at all. Right? I'm just introducing these carefully placed holes in terms. It's like lambda abstraction, but it is not lambda abstraction because it's carefully, in the case of the classical setting, it's carefully balanced. In the case of the intuitionistic setting, there's exactly one hole and it's filled exactly once. Right, so it's linear. In both cases, we have linear systems, and they're they're carefully accounted for, and we don't introduce all the subtleties of alpha equivalence and all of that mishigosh. So the holes are not, they're not variables, or they don't rise to the level of variables in this presentation. And that's by design. I don't want to have to deal with that. And we deal with the binding phenomena in sort of a module, right? So either we use the higher order abstract syntax, or we use the nominal Levere theories. So hopefully that all makes sense. Any comments or questions about that?
Yeah, for me, it's starting to make sense. So I have a question about constructing K.
Sure.
Do we immediately decide how we'll deconstruct K, or?
Well, K is a constructor. It's like in the case of the row calculus, K is par, right? So these types of say how you can form parallel compositions. So if you want to maintain certain kinds of isolation, then you form these parallel compositions according to these rules. So as an example, you can form a K like this, right? So if I have gamma together with T is of type tau, and I have U is of type tau prime together with delta, then I can form a K, right? In this case, this would be a par. It will be typed this way, right? And I'll have gamma as a part of the mix, and I'll have delta as a part of the mix.
And we are constructing K as a term.
Yes.
So we are in the type. We are saying how this is will be extracted. But not on the term level, on the type level.
On the type level, we're saying precisely that we've made a K, and the data is available for parallel extraction.
And if we want to say this is for serial extraction, we need what we need to do. We
so
still constructing K.
Yeah. So the types have to be different.
Okay, but the term is really the same, right?
Yes, that's right. So so notice that this one doesn't require a delta. So gamma, if this were in the intuitionist case, it's a little easier to see. There it is. So gamma thinks that T is of type tau and U is of type T prime, tau prime, right? Whereas in the case of parallel construction, I have T is typed tau independent of U being type tau prime, right? You have different typing contexts. Whereas in the serialized case, we have a single typing context that governs the whole thing.
Oh, I see.
Yeah.
Okay, thanks.
Sure. Awesome. Well, if there are any other questions, maybe we can yield back the rest of the time.
Can I ask just one question quickly? Sure. It's related to this talk that you mentioned of Ed Whitman about quantum theory and knots.
Yeah.
So on one slide he had like a hole where the tangle is in the knot.
Yes.
So is this really somehow similar to the K, because we can have different tangles?
Yes, it is.
On the same.
Yes, it is. And in fact, this is a point that I made explicit in my knots as processes paper, right? So there, the Kaufman bracket, which is a clever way to compute the Jones polynomial,
Okay.
is extremely nicely characterized. Let me see if I can make this super clear. No, I need some text. Okay, so suppose I have a process P. Sorry, let me put it this way. Suppose that K is equal to E R P. No, let me do it the other way around. P is equal to K of Q, right? So if P is a knot, and that's one crossing, that's a process that represents a single crossing, it becomes very easy to represent, to do the Kaufman bracket. So in particular, right, so the Kaufman bracket looks like this. Hopefully I can draw this in reasonable time.
And with this Kaufman bracket, we also have ability to categorize knots.
Well, the Kaufman bracket is a clever way of computing the Jones polynomial, and the Jones polynomial is a not invariant.
Okay.
All right, so let me make that and then do. Okay, so I'll do a bunch of these. Okay, and then let me go get. Okay. All right, so get rid of endpoint on this thing. Okay. Trying to be quick about this. All right, so here's. Oh wait. Oh, I thought it was connected. Okay, here's one edge. Okay, and here's the other. Okay, so there's a crossing, right?
Yeah.
And what the Kaufman bracket does is it says I've got some knot. So I need this thing. Okay. Really good. Okay, so I've got some knot, and inside the knot, right, I find this crossing. I need another.
And this is like on the graph, as you mentioned, a node with four edges?
Well, it's a tetravalent graph. Yes. So every knot diagram is a tetravalent graph. Okay. So the Kaufman bracket is that we're going to compute this in terms of recursively. I'm going to do the Kaufman bracket in which I have reconfigured it in the possible ways that it could be reconfigured, getting rid of this crossing. So there are a couple of ways that we can reconfigure this crossing, right? I can do it this way, right? So now I don't have a crossing. Sorry, I need another.
And this is in a sense different term, right?
Yes, right. And so I'm going to take that one, but in the case of knots are pictures, right? Or they're geometric objects. They're not terms. Right? So this idea of context is really not well specified in in knot theory, right? Darn it. Stop. There we go. But it is well specified over in programming language semantics.
Yeah.
Come on.
These are like different reductions, right?
Well, I wouldn't think of it as different reductions. I really think of it as different ways that, I mean, you might think of it as reductions. I think of it slightly differently. But it's like this, okay? So this is your Kaufman bracket, right? I think maybe you have to put a 0 in there as well, but essentially this is the recursive relation. Okay, so I can uncross this crossing by connecting, you know, horizontally or vertically. So I'm and then you have the oops. Come on. There we go. Try one more time. All right. And then but this is an endless recursion, right? So you need to ground this endless recursion. Oops. Come on. And so the base case for this recursion is that that, and let me put little. So if I have the unknot, which I'm using this particular symbol to signify. So here's the unknot. So that is equal to 0. Okay, so that's the definition of the Kaufman bracket.
I see.
Right? So now, what if I could represent a crossing as a process? Then what we're saying is that the whole knot, which is some process, is going to be equal. The way to calculate the Kaufman bracket then is to say that the whole knot, which is some process, P, is equal to some context that has at least that crossing, the process that represents that crossing. Okay?
I see.
Right? So now it's really easy to do the algebraic version of the Kaufman in terms of processes, because what we're going to do is we're going to take this K and we're going to replace Q with this uncrossing, and add it together. So let me use C for context instead of K, so we're not confused, right?
Okay.
All right. So then and this is some crossing. So I'll write that crossing as an X. Okay. So it's the process X that represents the crossing, and then there's a horizontal and a vertical, right? So what we're going to say then is that K of P, which is the Kaufman bracket, is going to be equal to, sorry, let me do this in a non-destructive way. So now K of P is going to be equal to K of C, in which I have replaced X with the horizontal thing together with K of C, where X has been replaced with the vertical one. Now that is precisely defined. We know exactly what that equation means. This one, the algebra, you're depending upon a kind of intuitive idea. Here, the algebra is crystal clear. We know exactly what this means. And then, of course, to get the base case, all you're saying then is just that K of 0 is equal to 0. There. So that's how to do the interpretation of the Kaufman bracket in terms of the Nazis processes interpretation. And the thing that's of interest is that we want. I'm fairly certain that I can take I can compose this interpretation with the Kovanov homology. And more recently, I've become convinced that I can use a similar approach to get an interpretation in processes of Feynman diagrams. So,
may I ask something about Feynman diagrams? I think Amadi mentioned about locality in Feynman diagrams as something that is, well, I'm not sure. So something that we don't want in that sense. So I'm just curious, do we, in this translation, do we have this locality or not?
well,
although I'm not sure.
the thing about processes is because names can be shared throughout a bunch of different processes. Basically, locality corresponds to isolation. Does that make sense? So when you're bounded inside a particular namespace, all interactions happen in a particular namespace. That namespace represents a notion of locality. Does that make sense?
Yeah, yeah. So we want to restrict locality as.
So if you want to make things more open, then you say that the namespaces are more porous. Right, a namespace that closes up everything, right? That's that can't intersect with something else, right? That namespace is contained. It's local. But if you have intersecting namespaces, then you have this kind of porousness, and that corresponds to non-locality.
I see.
Yeah.
yeah, this makes sense.
Sure. And so like, for example, you know, if you want to do some kind of EPR pair, what that really corresponds to is some kind of new scope. Right? They're joined at the hip.
Sorry, EPR pair. I'm not sure.
Einstein, Podolsky, Rosen. So
I'm not so familiar with that, so I'm sorry.
Oh, it's okay. So when two quantum states become entangled, right? Then you get this ability to have information shared across the two different states, regardless of how far they're separated. Right. So the notion of locality that's in namespaces is kind of splits the difference between locality in terms of spatiotemporal locality versus locality in terms of information flow. So those two things, like quantum mechanics says, you can have locality in terms of information flow, and that is decidedly distinct from locality in terms of spatiotemporal information.
I see.
Yeah. That's kind of the content of Bell's inequality.
Okay.
Anyway.
That was lots of information. Thanks.
Yeah, thank you, Greg.
Those are all fun questions. Yeah, no, they do relate to consensus. That's where things get really interesting, because it's precisely the quantum information flow that makes has lots of implications for consensus.
Yeah, one of my questions is it consensus like a knot? So I think you answered.
Yes, it is. Yes, there's something deeply connected between those two ideas. Yeah. Awesome. Well, I've got to get to stand up. So.
Great. Thanks, Greg. We appreciate it.
Oh, no, thank you.
Yeah, that was wonderful.
Yeah, I appreciate you guys asking good questions.
Have a good day, everybody.
Yeah. Ciao, ciao.
Bye-bye.